Good morning. I was just going through the recordings and I realized that we need to go a little deep into it on the mathematical aspects before we try to go further, right? And let us see what we are doing. We want to study the dynamic stability of the airplane. That means we want to study, you give a disturbance and see what is its behavior. That is how all the perturbed quantities are behaving. If they are coming back to 0, then we say it is dynamically stable, right? This is one. To do that, what we have done? We have developed what we call perturbed equations of motion, right? And you know by now that's a u dot, w dot, then your q dot. This equation where you have Fx perturbed aerodynamic force, Fz perturbed aerodynamic force in z direction, and perturbed aerodynamic moment. Okay, because we understand at steady state this m will be 0 because there is no such motion at a steady state because cruise is our steady state. But the moment I give disturbance, it will do all this motion, execute all this motion. So there will be perturbed moment. Then what we did, we know this Fx, Fz and m, they will function of alpha, alpha dot, q, delta E, etc. And we expanded it. And then we found those dimensional stability derivatives and plug in this equation to get a matrix. Okay, matrix equation of the form Ax equal to B. Okay, and then we know the characteristic equation is determinant of A equal to 0, and then we got the characteristic equation, the linear system, as Bs cube plus Cs square plus ds plus E equal to 0. We also studied a case based on the guideline that if the system has to be dynamically stable, that means no roots of this equation will lie in the right half plane of, if you see like this is imaginary, this is real, no root should be here. If any root is here, then it will be dynamically unstable. So, it will be that all the roots should be on the left hand plane. And for that, as per Routh criteria, the condition that all the roots will be on the left half plane is first is A, B, C, D, E all greater than 0, and then D into BC minus AD minus B square E should be greater than 0. This is typically Routh criteria, and those who are interested, they can read any book. We are using this condition to check the stability of the system. We have also studied one thing, that we have taken a simple case E greater than 0, and we have obtained a very important relationship when CMU, that is dCm by dm, or CMU, which is nothing but m1 dCm by dm, which is less than 0 for supersonic case, and we have seen what is its impact in defining the location of CG vis-a-vis neutral point. Okay? So, this we have done. Now, we are also trying to see if I agree that yes, if this system will be stable, if the roots are in the left half plane, the some are here, as we have been talking about, here roots are here. So, then how do I find those roots? We can find these roots by solving this numerically, right? There is no shortcut method to solve this equation. But what we have seen through one example where for a given airplane, the value of A was 675.9, B was 1371, C was 5459, D was 86.3, and E was 44.78. You know how to calculate this A, B, C, D, E using the dimensional derivatives or using inertia characteristics, mass characteristics, and the aerodynamic derivatives, etc. Right? This formula are listed, and you can refer them. What is important? When we try to exactly solve this equation, we found there are two pairs of root. One lambda 1, 2 is minus 1.008 plus minus j and 2.651. In another pair we got, this is minus 0.0069 plus minus j 0.0905. This result tells us something more than these numbers. What does it say? It says this fourth order equation can be product of two second order system. Right? That is very important, and it stands validated for most of the low speed, moderate speed aircraft. Right? So what is the meaning of this? Meaning this instead of handling this fourth order equation, you can think of it consists of two second order system. Especially I am talking about longitudinal perturbed equation of motion. Right? You could see what is this root? This is a complex conjugate, a complex pair. These are complex pair. What does this complex pair means? Means it must be oscillatory motion, and this oscillatory motion will go on growing or it go on reducing its amplitude. Who decides that? That is decided by the real part. As long as real part is negative, you know, because it's a complex conjugate, it will be oscillatory. But since this part is negative, the amplitude will go on decaying, because the amplitude will go proportional to e to the power real into t. The real part has to be negative for the amplitude to decay. So this is the two understanding we have got. So what it calls for now, that let us see what is the second order system and how do we model the second order system and how can take advantage of it. And that is exactly why I thought we will give a pause and go to a second order system and try to see a little more. Whenever we talk about second order system, you understand, it comes to our mind, it's a mass spring damper system. Whenever we think of a second order system, you all know this is the mass spring damper system comes to our mind, and that you know the equation is very popular equation, d square x by dt square plus c dx by dt plus kx equal to f of t. Right? This is one dimensional, the motion of a mass which is having a spring tied and have a damper. This is a very popular equation. So now, if I want to find the characteristic equation for this, for the homogeneous solution, the characteristic equation will be lambda square plus c by m lambda plus k by m equal to 0. You are all familiar with this. I divide this by m here, and then for x I write e to the power lambda t, and then put the derivative and you get the characteristic equation. Those who are not immediately on touch, you know, we find out by putting e to the power lambda t. So dx by dt will be lambda e to the power lambda t, and d square x by dt square will be lambda square e to the power lambda t. So you substitute for d square x by dt square, this one, for dx by dt, put this one, take common, and then you get the characteristic equation. Okay? And then by solving this equation, a quadratic equation, you can write lambda t equal to c by 2m plus minus under root c by 2m square minus k by m. I am sure you are familiar with this, right? You have done it in your some part of the course. And you also know that if c by 2m is greater than under root k by m, then this will give root will be real and negative. Okay, this is clear. If this is c by 2m is greater than under root k by m, then this m lambda 1, lambda 2 roots will be real and negative. And if c by 2m is less than under root k by m, then what happens? Then you get complex conjugate. Okay? complex pair or conjugate. And of course, natural question comes to our mind, what happens if C by 2m is equal to K by m? So lambda 1 and 2 is minus C by 2m. Okay? And then the solution for this case will be x of t will be equal to C1 plus C2 t e to the power lambda t. Right? I am focusing on this case when C by 2m equal to K by m, and the roots are negative and repetitive. So roots are like, the solution will be like this: C1 plus C2 t into e to the power lambda t. But you know, with the, as time goes to infinity, this product increases. But you know, the point is e to the power lambda t, when lambda is negative, that decays faster. So you come, your amplitude or x goes on decreasing. Okay, and this is typically the critical damping case. This is typically critical damping case. The difference between critical damping and overdamped case, which is here, this is overdamped case, right, is that in critical damping, the time required to come down to equilibrium is much smaller compared to an overdamped case. I am not talking about those things. Those interested, they can study it. What I am interested here is, for our sake, is that how do I handle a second order equation to find out its natural frequency and damping ratio. So let's say we have equation x double dot, which is by d square x by dt square, and c by m x dot plus k by m x equal to f of t, right? And let's say what we do is, we know omega n equal to under root k by m, which is natural frequency, which is the frequency with damping 0. Because in normal case, if you see this sort of a equation where we have written lambda 1 and lambda 2, you can write omega here, omega equal to, these are all the textbook material which you have already studied, and c by 2m square, right? But if damping is 0, if c is 0, then this is becomes omega n, which is nothing but under root k by m. Right. So that is exactly what I am writing here. And also we are doing one substitution, and that is zeta equal to c by 2 root km. Okay. Zeta is the damping ratio. And then if you substitute here, you can write this is as x double dot plus 2 zeta omega ns x dot plus omega n square x equal to 0. See, for k by m, omega n has been written. For c by m, we have written 2 zeta omega n, and x dot is here, and that is how I can write this equation. Once we agree with this, now if I take a Laplace transform, what happens? It becomes s square x of s plus 2 zeta omega n s into x of s. We are putting all initial conditions 0 plus omega n square x of s equal to 0. So our equation becomes s square plus 2 zeta omega ns plus omega n square equal to 0. Okay. So this equal to 0 is our characteristic equation for a second order system in Laplace transform using definition of zeta and omega n. Okay. So I thought, I've gone very briefly, but I thought it's worth mentioning this. Those who are interested, they can read further. So what is the message? Message is, so let me write s square plus 2 zeta omega ns plus omega n square equal to 0 is the characteristic equation for a second order system using omega n and zeta. Zeta is the damping ratio. Zeta is defined as damping ratio, and omega n is natural frequency. Okay. Now we come back to our problem. where we got the roots as, say, one pair of root I got lambda 1 2 equal to minus 1.008 plus minus j 2.651, correct. Another, of course, was lambda 3 comma 4 is equal to minus 0.0069 plus minus j into 0.0905. These roots can be also displayed like this graphically. So this is typically, you understand that one thing, that for longitudinal case, the solution for that s4 plus bs cube plus c square plus ds plus e equal to 0 will generally give two pair of roots complex conjugate. The moment you see two pair of root complex conjugate, you know this corresponds to longitudinal case. Okay? And you'll find roots are also given like this. Let's say minus 1.008, so something like this, and this is 2.651, one here, this is 2.651, this is imaginary, and this is real axis, this is of course negative, this is positive, and another pair is given somewhere here, where this value is how much? 0.0069, of course minus, and this much is, this value is corresponding 0.0905. So immediately you could see if this sort of a roots are displayed, you immediately know this is one complex conjugate, one complex conjugate. So there are two pairs of complex conjugates. Immediately you know that this corresponds to longitudinal case, and one of the pair has larger, very large negative real value, and another is smaller negative value. And you know, larger negative value means it will decay very fast. This understanding we should have. So now I come back here. So if this is this, whether given in that format or this format, I know it's second order system. I can immediately form the equation. How can I form? I say s square minus sum of the roots into s plus product of the roots is equal to 0, right? So what is the meaning of that? S square minus sum of the roots. Sum of the root means minus 1.008, and this plus minus this will get cancelled, so again minus 1.008. So this is into s, correct, plus product. Product means you can understand this will be minus 1.008 whole square plus 2.651 whole square. This will be equal to 0. So you will get equation of s square some number s some number equal to 0. Now you compare this with this to get zeta and omega n. Okay. So if I do a rough calculation, I can write this as approximately s square plus 2.016 s plus roughly 8 will be equal to 0. The moment I get this equation from these two roots, I will compare this with this. So I can write immediately, you could see here that I could write 2 zeta omega ns, s will not be there, will be equal to 2.0165, and omega n square will be equal to 8. So omega n square equal to 8 means roughly omega n will be equal to 2.836 per radian, radians per second, and radians per second, right? And zeta I can find out using this equation as 0.355. So simple. So what is the message? Message is, if you have an aircraft, if you know the geometry, form that equation s4 plus bs cube plus cs square plus ds plus e equal to 0. A, B, C, D you can find out from geometry and the aerodynamic derivatives. Then numerically solve it. You will find two pair of such equation will come, and you find out zeta and omega n. Only understanding now you should have from this number is what is this happening in the airplane if I give a small disturbance. What happens if there is a disturbance? The two predominant way the aircraft can respond, one is short period type, that is disturbance immediately damps out, whose real negative root will be large, that will behave like this. And the roots where real negative is negative but not that large, so that is something like this. So typically for an aircraft in longitudinal characteristics, it is dominated by two modes. One is short period mode. In that mode we assume that things happen so fast that the change in the u is negligible. But in the phugoid mode, long period mode, it almost goes like this, the change in kinetic and potential energy. The classical book talks about the alpha almost remain constant. There is a debate. But let's see, you understand that some sort of a kinetic energy and potential energy conversion is there, and it takes longer time to come back to equilibrium, which you could see easily from the second equation. If we again find out the root for this lambda 3, 4, if I solve that equation, which is here, a similar way what we have done here, then we will get values as omega n is equal to 0.091 radian per second. You should solve yourself, and you can expect one question in the exam of this nature, 0.076. You could see that zeta is 0.076, but it's 0.355. So it is a highly damped compared to this. And this is typically, this is closer to a short period type excitation, and this is like a phugoid type. Okay, so phugoid, 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 and this is short period. We'll explain what is phugoid and short period approximations, but I thought we'll solve this example, and that will throw a lot of light. You'll understand what you are doing. Don't get bogged down by big equations. Those equations, once derived, is known. You need not remember this, but I have to understand how to utilize those equations, right? Okay. We talked about short period and phugoid. We'll try to see how this 6-DOF derived short period equation of motion for longitudinal case can be utilized with appropriate approximation to get omega n and zeta expression for short period as well as phugoid mode. But that will be in the next class. Okay? Thank you.